Yes. Yes. So microphone. Well, I don't know. So do we wait until? Oh. Yeah. Oh, it works. Huh? Okay, it's better, yeah. Thank the organizers for inviting me and for giving me the opportunity to give this talk. So today I'm going to talk about universal terms in the overlap of Néel and XXZ ground state. And yeah, so the outline of my talk is as follows. I will start with a brief introduction where I try to motivate why the overlap of the Néel state with the ground state of XXZ model is interesting, and why we are interested, why the large L scaling, so the scaling in the thermodynamic limit, can be used to get information about certain entropies and is connected to, boundary CFTs. Then I will introduce the anisotropic spin 1/2 Heisenberg chain just to fix the notation, and then the technical part of my talk is about these overlaps of the Néel state and how to compute these overlaps in the thermodynamic limit. And I will show you that there are two techniques which will be used to get information out of these overlaps. And the first one is a computation of Fredholm determinants, and the other one is these techniques of nonlinear integral equations for spin chains of finite length. And we will compare at the end with Euler-Maclaurin formula and what are the advantages of the first technique. And at the end I will summarize and conclude. So this work was done with Jean-Marie Stéphan, who is at the Max Planck Institute of Physics of Complex Systems in Dresden. And I'm also grateful to the Max Planck Institute, where we started this project a couple of months ago. So let me tell you why we are interested in the overlap of the Néel state with the XXZ ground state. So these overlaps, they appear in the Renyi-Shannon entropy, and they are also connected to boundary CFTs. So let me briefly discuss these two last points. And so there are different entropies from which you get some information of your underlying system, say a spin chain. Yeah? So the main example is the entanglement entropy, and so it is kind of a tool for characterizing many body quantum states. And as you probably know, there is a logarithmic divergent term in the von Neumann entropy, and from which you get the central charge of the spindle of the critical chain, and it's just a prefactor. I think it's C/3, and this entanglement entropy can be also used in higher dimensions to detect topological order. So I won't discuss this because here we are interested in a 1D system, in particular the XXZ spin chain. So, and there are other entropies from which you get information of your low energy sector of your chain. For example, the Reni-Shannon entropy, which is defined in this way. So it is the logarithm of a sum over a whole basis of your Hilbert space of the overlap squared to the power n. And so there are certain properties. One property is that the usual Shannon entropy, which is written here in the lower right corner, can be obtained by taking the limit n to 1. So you just apply L'Hopital's rule and then you easily get this expression. And there are other two simple limits of this Reni-Shannon entropy. So one very trivial one is the limit n to 0. And then you get the logarithm of the dim-Hilbert space. Another trivial one is the limit n to infinity. And then this Reni-Shannon entropy reduces to the logarithm of the overlap square of the state psi and the state m in the basis, which is maximally overlapping with this state psi. So now we will focus on a choice of psi, namely the ground state of our spin chain. And and for the basis, we usually choose the local spin basis. So, and from this, or in particular from the S infinity, this gives universal long distance properties of your chain, and it also probes the system globally. So for the entanglement entropy, you always have to choose a subsystem of your chain. So, and this is not necessary here. So this is one advantage, and it is also connected to a certain entanglement entropy of a 2D system. And so analyzing this Reni-Shannon entropy also then allows for an investigation of the entanglement entropy of this 2D system. And so as I said before, we are interested in the large system size scaling of this logarithm of the overlap squared, and or actually of this entropy. And for the usual Shannon entropy, this can be obtained. So here the part proportional to the system size is just dropped, and the O of 1 constant, the order 1 constant, is just the logarithm of the compactification radius of this free compact boson. So this is a result obtained earlier, and now we will see if it's possible to get something out from the XXZ spin chain. So this is a Hamiltonian of our chain for finite length L. So we assume periodic boundary conditions here, and then there's a conjecture for this universal constant beta here. So you know that the entropy behaves as there's this entropic part, and then there's a universal constant plus subleading corrections. And for this universal constant, there's a conjecture that it behaves like this. And then in the limit n to infinity, the second term just vanishes, and you get the log of R. So, and this was supported by numerical calculations based on exact diagonalization and some Landshaw's method, and this is possible up to L32, which is not very large. Yes, please. So universal with respect to the low energy sector. So you identify your conformal fields. I will come to this point. Like, yes. We will see that it is, or that it is connected to some conformal field series, and in this sense universal. So if you had another conformal field theory, another model which scaled to the same conformal field theory, then you would get the same constant. Yeah? Okay, so, and yes, so as I said, there's a connection to some partition functions and to boundary conformal field theory. So the low energy physics is captured by Luttinger liquid theory for the XXZ model. And so now I would like to emphasize that there's this correspondence between 1D quantum systems and 2D classical systems. And so for a state, say an arbitrary state A, which doesn't have a non-zero overlap with the ground state, the operator e to the minus tau h acts in the limit tau to infinity as a projector onto the ground state. This is written here. And then if you just choose A as a Néel state, you can use this equation to derive this first equation here. So the overlap squared is given by a ratio of a product of two terms. Two times is, so it's a square here, divided by a similar term. And these guys here can be interpreted as partition functions with certain boundaries. So here the boundary is fixed by the Néel state, and this partition function is a partition function of a cylinder with length L, with circumference L and length tau. So this is a direct connection of these overlap squared to this ratio of partition functions. And so there was one assumption in the paper by Cardi that these Néel boundaries, fixed here by the Néel state, they renormalized to a conformal invariant boundary, so which is believed to be a Dirichlet boundary condition. And then for this CFT you can compute this ratio explicitly, and it turns out that it is a prefactor square root of k times e to the minus alpha L. And so maybe this answers your question, yeah? So that is really related to conformal field theory here. And in this context, these prefactors of this exponential decay, they are called sometimes G factors, and they of course depend on the CFT and on the boundary conditions, but on nothing else. That's a claim. So now we want to try to prove the explicit form of this prefactor here, that this is indeed square root of k first, and on the side effect we get also information about this kind of non-universal part alpha if we choose the XXZ chain, and also on higher on subleading corrections here to this expression. Okay, so this is a kind of introduction, and now I just formulate the goal. So we would like to prove that for the Heisenberg spin chain, anisotropic with an anisotropy term delta here, and we will mainly focus on delta in the critical regime, so it means absolute value of delta is smaller than 1, and that if you then compute the overlap squared with of the ground state of this Hamiltonian with the Néel state, that the order 1 contribution beta is given by minus 1/2 log k, and in the critical regime, and in the massive regime it is given by 1/2 log 2. And also we would like to compute delta as a function of the anisotropy. Yeah? Maybe I can just as a guideline I state the goal. So it is this overlap squared is given by minus alpha L minus beta, so it is plus 1/2 log k plus O of e to the minus delta with a positive delta. So you're right, sorry. Yes. So we would like to prove that this is indeed the order 1 correction, and maybe we get also some. No, we will get also some information about this higher subleading corrections. Okay. So the idea is that we take in the Rayleigh-Shannon entropy the limit n to infinity, and we get this expression, and this is stated here at the blackboard. and we identify as a state maximally overlapping with the ground state, the Néel state, which is indeed true. You can check it by finite size analysis. And it is always for any system size that it is a state which has a maximal overlap with the Néel with the ground state of XXZ. And then we will I will show you that there is an efficient formula for this overlap, and which can be analyzed in the thermodynamic limit. So this efficient formula for this overlap of an eigenstate of the Hamiltonian with the Néel state was derived 2 years ago, and can be used to get this finite size scaling of this expression. And so we will faced with two problems when writing down the overlap formula and taking the logarithm. So the overlap formula contains basically two terms. One is a ratio of Fredholm determinants. So we have to do a calculation and to see how Fredholm determinants can be computed. And the other one is a prefactor, which then, if you take the logarithm, becomes a sum over a certain function f, with which depend on one single beta root. Okay, so before I'm going to present the overlap formula, let me introduce the model. So just to fix the notation. And as I said, we will focus on the antiferromagnetic gapless regime, but most of the calculations can be also performed in a very similar way for the gapped case, just by replacing the signs by sincs and the sincs by signs. We will see. So this is easy. So, so this is a Hamiltonian. It depends on the length of the chain, capital L. And it is anisotropic with anisotropy delta, which we write as a cosine gamma. And we assume periodic boundary conditions. And yeah, so as you know, there's an algebraic beta structure for this model. So there is an R matrix which allows for this RTT-TTR relation and is written in terms of the anisotropy gamma and the spectral parameter lambda in this way. And then you define a monodromy matrix as a product of L many Lax operators, which can be then written as a 2 times 2 matrix. The matrix structure is then in the auxiliary space, and A, B, C, D are operators acting in the Hilbert space of the spin chain. And then the Lax operator is written in terms of these local spin operators in this way. And at the end, what you find from Young-Baxter symmetry is that if you look at the trace of the monodromy matrix, which is called the transfer matrix, it commutes with for all spectral parameters lambda and mu. And this is the heart of integrability, actually. So then we choose a pseudo vacuum state called 0, which is a ferromagnetic state, so all spins pointing up. And then one can prove that the C operator acting on the state gives 0. So it is the monodromy matrix has a triangular structure. And then you define states as a product of MB operators acting on this vacuum state. And these states are called beta states. Okay, so far this is just a formal definition, but then so you can prove that these states are eigenstates of the transfer matrix as long as the parameters lambda j fulfill these beta equations. So this is a well-known fact from beta ansatz. And so we will focus on the ground state, which means for zero magnetic field, so which means that m is L over 2, so there are L over 2 many of these rapidities or beta roots, and they just fulfill these set of equations. And for the ground state, we have the one knows that all the lambdas are real. So this will be important later. But here for this is actually if you solve these equations, you get many different solutions, and these solutions, and if you insert it here, you get eigenstates of your Hamiltonian. So that's the logic. And well, so as I said, we are here in the zero magnetization sector because we are interested in the overlap with the Néel state, which is in the zero magnetization sector. So the state we are overlapping with has to be also in the sector to give non-trivial results. And so we also introduce one notion. So it's the term parity invariant. So we call a state parity invariant if it has this, if the set of all the lambdas has this symmetry. So this is a reflection with respect to the origin, and then if this is fulfilled, then we call it parity invariant. So then, since we are also interested, so be careful here, these states, they are not normalized yet, and at the end we would like to compute the overlap of the Néel state with a normalized ground state. So, and then that's why we also need the norm, and the norm of the state, of a beta state, this was a formula conjectured by Godin and later proven by Vladimir Korepin. And so it can be written as a prefactor times the determinant of a certain matrix G, and this matrix G is explicitly given in terms of these solutions to beta equations. So well, you could say, well, so then let's solve the beta equations and plug everything in. So, and then we have the ground state explicitly given, but the problem here is that applying these B operators to this vacuum, L over too many times, gives at the end exponentially many terms. And you cannot handle this. So that's why it is really useful to use this norm formula for the overlap. And so, so before I come to the overlap formula of the ground state with the Néel state, let me just briefly sketch some properties of the ground state in the thermodynamic limit. So you can write the beta equations in the logarithmic form, which look like this, where I, J are some quantum numbers. And for the ground state, they are symmetrically distributed with respect to 0. And these are the quantum numbers which are as close as possible to 0. And so then the thermodynamic limit is can be performed in the following way. So you just replace here in this equation the ij divided by L by a variable x, the lambda j by a variable lambda, and then via these equations, lambda is a function of x with the property that if you insert ij over L for the variable x, you get the lambda j back. And then the root distribution for a finite L can be written in this way. And so this can be taken as a definition for the root grounds, so for a root distribution at finite L, and then if you plug in here the ground state roots, you get your exact row of lambda, sorry. And all these functions here, phi and a, they are explicitly given in terms of the anisotropy parameter gamma. Okay, so then you can, if you're, so for the ground state, you have L over too many beta roots lambda, and you can, for later purposes, we need the scaling of the largest rapidity and the scaling of the smallest rapidity. And the smallest rapidity is the lambda corresponding to the index L over 4 plus 1, and it is just gamma divided by L for large L. And the largest is scales as log of L, basically, with a prefactor gamma over pi. And then in the thermodynamic limit, it means that lambda goes to infinity. So it means that you can replace here the sum by an integral and integrating from minus infinity to infinity to get the thermodynamic limit of the root distribution for the ground state. And this can be solved easily by just, for example, doing the Fourier transform of this equation, and then you get the row of lambda as a solution of this linear integral equation, which reads as 1 over 2 gamma cosh pi lambda over gamma. So, and since we need this later, I just write it down. Pi lambda over gamma. So, that's because we will need it when analyzing the overlap formula with by means of the Euler-Maclaurin formula. So, which will be at the end. So that's why I just keep it on the blackboard. So now, so for the Néel state, there is this nice formula for the overlap of the Néel state with an arbitrary beta state, on-shell beta state. And so this has the following structure, right? It has a prefactor depending on the lambda j's just by a product of a function which depends on a single beta root and times a ratio of two determinants. And these determinants are very similar to the, or the matrices are very similar to the matrices from the norm. So you can, so this G plus and G minus are given here. It is just 1 plus and then k of lambda j minus lambda k plus minus and then the sum of the two beta roots. So this comes from the fact that the proof, or that there's a deep connection of the proof of this overlap formula to some beta ansatz with reflecting ends. So in this sense, the structure is preserved by this minus lambda k, and here so here the difference of the roots and here the sum of the roots. So and the kernel k is just given as before. So it is the sine of 2 gamma divided by sinh of lambda plus I gamma times sinh of lambda minus I gamma. And here the matrix is of dimension L over 4. So we are only taking the positive beta roots into account. Since the state is parity invariant, this is also the whole information of the state. Okay, so yeah, well, so here we are focusing, so L over 2 is even. Yeah, sorry. Impossible, exactly, but it is also possible to treat this, and then you get a determinant of the same structure where the first column and the first row is slightly different. Yeah, so because you have to take care of this root at 0. So this is one of the 3 remarks here, that the case L over 2 odd can be treated similarly. So, and we did it also 2 months later in this work. And so anyway, so we here, as I mentioned, we are only taking the positive beta roots into account, since the ground state has the symmetry of parity invariance, and all these beta roots are real for the ground state. No, we are interested in the ground state here. The roots. So it is, they look really like for finite L. This is the distribution in the thermodynamic limit, and if you are at finite L, they look like, so say L equal 16, they would look like this. These are the ground state roots. Yeah. Only real. So, of course, XXZ allows also for string solutions, but here we are interested in the overlap with the ground state. Okay, so so here we are going to analyze these two terms. So first we will look at this ratio of determinants, which becomes in the thermodynamic limit a ratio of 2 Freitom determinants, plus some corrections, which are of order L to the minus delta tilde, with a different delta tilde from this formula at the blackboard here. Yeah, so this is not the same, because here the corrections are just of different type. And here the operators k hat plus minus are the corresponding integral operators to these kernel functions. And in the second step, we will analyze the logarithm of the prefactor, which can be written as a sum of a certain function f of lambda j. And for just convenience, we write this as 1/2 of the same function f and the sum is then over all rapidities. Yeah? So the function f is even here. So f of lambda is just a logarithm of this prefactor term, which can be rewritten by using just some trigonometric relations, and here you explicitly see that this is a real number. Okay, and how to treat the sums of a function of a single beta root lambda j, and then summed over all beta roots. So there are two ways of doing it. So either you can use techniques of nonlinear integral equations by choosing a contour surrounding all the beta roots and defining a certain auxiliary function. Or you could just say, well, let's do the sum and let's approximate it by Euler-Maclaurin's formula, and then the sum is replaced by an integral plus order 1 correction plus higher corrections and so on. And we will see that for this certain function f, this doesn't work out very well. So it works a bit, but not completely. So I will come back to this later. So let's first do the ratio of the Freitom determinants. The kernels are given explicitly here by these, the matrices are given explicitly in terms of these kernels. And this integral kernel acts in the following way on a function f. So it is an integration from 0 to infinity. Yeah? So this is because we only take here the positive beta roots into account. So that's why it's an integration from 0 to infinity. But now we would, to compute it efficiently, numerically, so we would like to go back to a integration over the real line. So, and that's why we use the following determinant formula. So the determinant of a minus b times the determinant of a plus b is a determinant of a double-sized matrix with entries a, b, b, a. So this is a block structure. And this is a very useful relation, which can be used now to take also the negative beta roots into account, yeah, by expanding this ratio in a certain way. So, and then also we use the fact that the determinant of the inverse is the inverse of the determinant, and so here the ratio of the two determinants here can be written as a determinant of the identity operator plus k hat, where now k hat acts as a integral operator now integrating over the whole axis with a kernel k of k gamma. And here then you have a det squared, and this can be also simplified using this relation by det identity operator plus I plus k hat to the minus 1 times k tilde. And k tilde is now an operator also acting by integration over the whole real line, now with certain theta functions and also some combination of the kernels. Okay, so and this can be, so this Freitom determinant can be computed. Yes, this is a unit step function, yes. So if lambda times mu is negative, this term is enters, and if lambda times mu is positive, then this term enters. Yeah. Okay, and this Freitom determinant can be computed efficiently on a computer. So for the convolution integrals, you just use the Jacobi-Gauss quadrature method, and then you discretize this integration with respect to this Jacobi-Gauss weight. Yeah, so this is a certain algorithm which is implemented in many programs. I use just Mathematica, and it is implemented there. And then the determinants of the matrices are computed just explicitly as a determinant. So you discretize your interval by just a few points, and then you compute the determinant. So, and just the details of the numerical method here I used is that first you have to introduce a cutoff. That you cannot integrate from minus infinity to plus infinity, so you introduce a cutoff lambda. Say lambda is 10, and then you choose 100 points, and then you compute the determinant of a 100 times 100 matrix, and then you increase the cutoff, you increase the number of points, and you see that you get very fast convergence. So 16 digits. So, and the result is just that the log of this ratio of determinants is, in the critical regime, it is -1/2 log k, and in the massive regime, it is 1/2 log 2. This just comes out, and it is precise, up to 16 digits. And we did this for several deltas, and so confirmed that this is indeed the correct formula. So now we come to the analysis of the prefactors. So we define an auxiliary function, A of lambda, in the usual way. So this is the whole business of this quantum transfer matrix method. So this is auxiliary function A. And the main property of this function A is that if you plug in a beta root, that it is just -1 due to beta equations. And there are two other important properties which will be needed if you derive later some integral equations, namely that alpha is small if the imaginary part of lambda is close to gamma over 2 and the real part close to 0, and it is huge if it's the other way around. So if the imaginary part of lambda is minus gamma over 2 and the real part is close to 0, then the function A becomes large. Anyway, so for this function A, one can show that the sum of beta roots can be represented as a contour integral, which can be very easily seen. Yeah? So the contour C encircles all the beta roots, and exactly there, this function has a single pole, and then you take just the residue, and so the A prime then cancels, and you get f of lambda j. Very easy. And then you do integration by parts, and you have the logarithm of 1 plus A times f prime. You have to be careful if you do the integration by parts. The function f, for example, if it's a constant, then you get some extra contribution from the branch cuts of the logarithm of 1 plus A, which can be easily seen if you choose just f as a constant function, say 1. So then you get here L over 2, but here you would get 0. And this is wrong. And so it means that you have to take the surface terms into account. Okay. Another important property is that this auxiliary function A fulfills a nonlinear integral equation, which was derived by Jens Dammerau, Frank Gömmern, Niels Peter Hasenklever, and Andreas Klümper in Wuppertal, and has the following structure. It is the logarithm of A is a constant plus some driving term, and minus a contour integral of log 1 plus A. So the usual structure of these nonlinear integral equations with a given kernel K as before. And but we would like to get some numerical values at the end, and contour integrals are not good for numerics. So we have to straighten the contour in a certain way. So we define two functions, B, which is now the inverse of A of x minus I gamma over 2. So I take here the inverse because then the function B is small around the origin. And here I define another function B, this should be B bar, sorry, the bar is missing here, B bar, as A of x plus I gamma over 2. And this is also small for real x around the origin. So, and then with these two definitions, one can, here the B bar is again there, and so then can derive a set of two nonlinear integral equations, coupled nonlinear integral equations with an explicit driving term and convolution integrals. And here you have B and B bar, and here you have also B bar and B. So, and the new kernel F has a following structure. It is a Fourier integral of this certain ratio of sinh and cos. Okay, so and to compute this on a computer, so it is really convenient to go to the Fourier space. So the convolutions are then computed by the making use of the Fourier transform and the fast Fourier transform algorithm. And then you solve these equations iteratively. So first you set all these b's to 0, so then the log b is more or less given by the driving term, and then you plug this to the right and compute new b's, and so on, and so on, and so on. And you, after a few steps, you are done. You know your functions up to arbitrary position, arbitrary position basically. Yeah? And okay, good. And this can be done for any system size well, let's say smaller than 10 to the 14. So this is way bigger than 32. And because the system size only enters here in the driving term, so there's an explicit dependence on the system size L, and if L is very large, it doesn't matter. Yeah, so you can solve these equations for any L basically. Okay, so this is an important fact, and now we would like to sum over these function f, and so we split f first in 3 terms, and here, as I mentioned before, if you have a constant, then you have to take it explicitly. Yeah? So because then you cannot apply the integration by part, but for the other terms you can, and then you will see that this f prime has a pole at 0. But as I mentioned before, the contour C encircles only the ground state beta root. So it goes, you have to choose it here in this particular case, for example, like this. So without this. But now we would like to, so and it goes this direction, and now we would like to straighten it to this and to this, where here is minus gamma over 2, and this is gamma over 2. Okay? So it means that we get, if we straighten the contour, we get an explicit contribution from this pole. So it is then a clockwise integration. So that's why you get this minus sign here. And the function which shows the pole. Yes, so first the contour C is, this is a contour C. And now we would like to use the functions b and b bar, which are defined on this horizontal lines for real arguments. And so we would like to use these functions, which we know, to arbitrary precision. And so that's why we have to deform the contour. And then this pole, which was before outside the contour, is later inside the contour. So, and then you have to subtract this extra contribution to make the equality being an inequality. Yeah. So, and this is the extra contribution. So it is minus 2 times log 2, because a of 0 is just 1. Okay, good. And then after further manipulations, so now we deform the contour in the following way, and then we can plug in just on this axis here the definition of b, and on this axis the definition of b bar, and use the integral equations for b and b bar, and then we derive for the sum of this function f of lambda j over all beta roots the following expressions. So it is L times the function f divided by 2 gamma cosh pi x over gamma, which is actually, sorry for going back, so this is the derivative of this function. And you see that it is exactly the rho of x. And this is also what you would expect. So it is f of x times rho of x times L. And then you get the finite size corrections, so order 1 corrections. And they are expressed by this double integral over the function log 1 plus b, which we know, and the function f prime, which we also know. Okay, and then we compute this. And the first term is just the extensive part. And the second term gives then for very large L and up to very high precision this numerical value minus 2 times log 1 minus gamma over pi for several gammas. Okay, and then altogether with this value for the log of ratio of determinants, we get for the overlap squared, if you plug in everything, you get minus L alpha plus 1/2 log k. Okay, quad error demonstrandum. So where alpha is just the integral from 0 to infinity, f of lambda rho lambda d lambda. So it is really the distribution from the contribution from the root distribution, and f is just the prefactor function. Okay, that's it. So we have shown that we have computed this constant alpha. check. We have checked this, and now what's with this term? This can be also easily done. So first, one observes that the function log 1 plus b, it has some bumps. Yeah? It is, if you draw log b, it is 0, and then it has a bump here, and it has a bump here. So. Yes, yes, it depends on anisotropy via via rho and also via f. Yeah, so there's also. Yeah. So, oh, good question. Yeah, so I could later. Let's discuss after the talk because I have it. Yeah, it can be easily computed actually, but okay, sorry. Yeah, no, I should have put it here into the talk. Yeah, well, so the range of, but it can be computed. Yeah, alpha is positive. Yes, alpha is positive always. Okay, so the exponent delta we get as follows. So first we observe that the function log 1 plus b, sorry, I did it wrong here. So ln 1 plus b, it has bumps. And these bumps are at gamma over pi over gamma, sorry, ln 2l of pi. Somewhere around here, and the function f is peaked around 0. And the kernel which connects in this equation, the function log 1 plus b and the function f prime, it decays exponentially. And the exponential decay depends on the poles of this Fourier transform of f. So there are this function has certain poles, and from these poles you can read out the exponential drop-off of the kernel f. And from this exponential drop-off, if you shift one of the arguments exactly by this value where the function has a bump, you get L to the power, and if you plug it in here, to the delta, and delta then is the minimum, so it's 1 if it drops off like this, and it is 4k minus 2 if it drops off like this. So, and this can be also easily drawn, so this is if you draw it as delta 1, 0, delta of gamma, which is a function of delta, it is like this. Okay. Yes. Well, in the limit gamma to pi, I don't know. So this is a nasty limit. Yeah, later. Okay, so now we have everything. Yeah, so actually, so we also have here the corrections, and now we would like to see. Well, this was a really advanced method to get all this information, but is it possible to get it straight by applying Euler-Maclaurin formula? This is the Euler-Maclaurin formula. This is a formula which connects the sum of a function f, or which expresses the sum of over a function f with its integral from m to n plus corrections, where the bk's are the Bernoulli numbers. And well, so if you have a composition of functions, so f now is a function of lambda which depends on x, and x takes basically integer values, ik over L, then the Euler-Maclaurin formula reads as follows. So it is the sum of f of lambda k is this extensive part, L times this integral, plus direct corrections, order 1 corrections from the boundaries, plus hopefully corrections of order 1 over L to the power 2k minus 1. And if this were true, you could use it easily, but it's not. Yeah? So the problem here is that this rho L of mu, also for large mu, it decays. Yeah. So and then this product L times rho L of mu is not big anymore. Yeah. So and this is what I said. yeah, this is true for the upper boundary, and for the lower boundary, this f of mu is logarithm of epsilon, basically. And logarithm of epsilon, if you take the derivatives, then it's also, it gives 1 over epsilon to the power 2k minus 1, and then L times this epsilon is again not a big number. So, but, let me skip this. So, so this has a logarithmic divergence. So this function here has a logarithmic divergency, as I mentioned. So, and then at the lower boundary, you can apply this derivative to log L 2k minus 1 many times, and then you get epsilon to the minus 2k plus 1, and then at the end you get this expression to the power 2k minus 1. Epsilon behaves as gamma over L, rho behaves as 1 over 2 gamma at 0. So it means that this value takes, or this bracket here takes the value 1/2. So, and then this series, or with this factorial factor here and this factorial, they cancel more or less. And then this can be, if you look in literature, this is just an expansion series of the log gamma function at the value x equal 1/2. So which is 1 minus log 2. Yes. So this is, but if you look at Wikipedia, Euler-Maclaurin, this is one example where, yeah. So, or no, this isn't at Wikipedia, but this was in some literature of logarithmic divergency and Euler-Maclaurin. So this was a paper by some mathematicians where I found it. So anyway, so this this can be used, and then you have also a contribution from the integral from 0 to epsilon of this, and the constant correction of the Euler-Maclaurin formula, which is just 1 plus subleading corrections, and therefore you can sum up the log of tanh squared minus the extensive part is just minus log 2. Okay, this is for the lower boundary. But there are also logarithmic divergencies at the upper boundary of the integration interval. And these cannot be treated because we don't have the function rho L, which is needed here in the Euler-Maclaurin formula. We don't have the 1 over L corrections to it. And that's why it's not possible. But luckily, in the massive regime, there is, so the largest rapidity is bounded by pi over 2. And then you don't have this problem. And then everything applies, and you get out the correction log 2, the Euler 1 term, log 2. And so together then with the log ratio from the Fredholm determinants, you get log 2 minus 1/2 log 2. No, well, 1/2 log 2 minus log 2, and then you get out this term. So it is, again, the log overlap squared is the extensive part minus 1/2 log 2. So it doesn't depend on the anisotropy, which maybe reflects the symmetry broken nature of the ground state. So it is gapped. Okay, so I think that's it. So let me summarize. So I've shown you that there are some universal terms in the Shannon entropy and in the ratio of partition functions with certain boundaries, which can be then connected to the underlying conformal field theory. And then I used an algebraic beta-based overlap formula to get an exact prediction for this universal order 1 term. Okay, so moreover, we also got an explicit expression for this coefficient alpha, and we also get an explicit expression for this exponent delta. Sorry. Of course. Sorry. For this expression delta, yeah, which gives a higher order subleading corrections to this first 2 terms. And yeah, so the used method was some efficient algorithm to compute ratio of the Fredholm determinants. and this is also applicable to zero field situation, yeah, so where it might be difficult because usually these integrations then are from -infinity to +infinity, but as I have shown, this is doable, yeah, and gives the correct answer. Yeah, and that the Euler-Maclaurin formula is not applicable in the gapless regime because you have a logarithmic divergency also at the upper boundary, but in the massive regime you don't have this. All rapidities are bounded, and then you get the correct answer for this order 1 correction term. So possible extensions to this is maybe that one changes the boundary conditions of the CFT and then identifying this with a certain state, computing the overlaps and so on. Or just maybe investigate some other models where the overlap formula is already known. So for example, Lieb-Liniger, we know an exact expression for the overlap of the ground state with a BSC-like state. Okay, so thank you for your attention.